Have you ever wondered how quantum computers could break the internet? It's a question that's been boggling the minds of tech enthusiasts and cybersecurity experts alike. Quantum computers, with their immense computational power, could potentially dismantle the internet's security infrastructure. But how? That's what we're about to explore. So buckle up and prepare for a thrilling journey into the realm of quantum computers and their impact on the digital world. Stay tuned as we delve into this fascinating topic. To understand how quantum computers could break the internet, we first need to understand what quantum computers are. Unlike classical computers, which process information in binary form as ones and zeros, quantum computers use quantum bits, or qubits. Qubits can exist in multiple states at once thanks to a feature of quantum mechanics known as superposition. This allows quantum computers to process a vast amount of information simultaneously, making them incredibly powerful for certain types of calculations. Another key feature of quantum computers is entanglement, a phenomenon where pairs of qubits become interconnected. This means that the state of one qubit instantaneously influences the state of another, no matter how far apart they are. This entanglement can potentially enable quantum computers to solve complex problems more efficiently than classical computers. But what kind of problems are we talking about? Well, quantum computers excel at tasks like factoring large numbers and simulating quantum systems. This might not sound too exciting, but these capabilities have far-reaching implications. For instance, most of the encryption algorithms that secure the internet today rely on the fact that factoring large numbers is hard for classical computers. But for a quantum computer, it's a walk in the park. This means that in the future, quantum computers could potentially break many of the encryption schemes we currently rely on to keep our online data safe. However, it's not all doom and gloom. Quantum computers also hold the promise of creating new, more secure encryption methods. Techniques like quantum key distribution, or QKD, use the principles of quantum mechanics to create keys that are virtually impossible to crack. But more on that in the next scene. So in essence, quantum computers are extremely powerful machines that use the principles of quantum mechanics to process information. They have the potential to disrupt many fields, including cryptography, the science of encoding and decoding information. Now that we have a basic understanding of quantum computers, let's explore how they could potentially break the internet's security. Quantum computers pose a significant threat to the internet's security due to their ability to break asymmetric encryption algorithms. Now let's dive deeper into this. Asymmetric encryption algorithms such as RSA and ECC are the backbone of internet security. They rely on mathematical problems that classical computers find incredibly difficult to solve, like factoring large numbers. This difficulty is what keeps our data safe when it's whizzing around the internet. But here's the catch. Quantum computers laugh in the face of these problems. You see, quantum computers are not just faster versions of classical computers. They operate on a fundamentally different level, using the principles of quantum mechanics. This makes them incredibly efficient at solving certain types of mathematical problems. Problems that, for a classical computer, would take longer than the age of the universe to solve. A quantum computer could potentially solve in just a few seconds. This is where the threat to internet security comes in. If a quantum computer is powerful enough, it could crack our current encryption schemes, exposing the sensitive data they were designed to protect. This includes everything from your credit card information to state secrets. But is all hope lost? Are we doomed to a future where no secret is safe? Not quite. Interestingly, while quantum computers pose a significant threat to current encryption methods, they also offer a potential solution. This is where quantum key distribution, or QKD, comes into play. QKD leverages the principles of quantum mechanics to create virtually unbreakable encryption, but we'll dive deeper into that in the next scene. So, while the rise of quantum computing certainly presents challenges to our current internet security infrastructure, it also provides opportunities for advancements in encryption technology. The key will be to stay one step ahead of the game, adapting and evolving our security measures as quantum computers continue to develop. While this sounds alarming, quantum computers also offer a solution. Quantum computers can provide enhanced security through a process called quantum key distribution, or QKD. In the world of cryptography, QKD is a game changer. It's a protocol that uses quantum mechanics to secure communication channels, allowing two parties to create a secret key that only they can know. You see, it's all about encoding information in quantum states, such as the polarization of photons. Now you might be wondering, how does this make communication more secure? Well, the beauty of QKD lies in one of the fundamental principles of quantum mechanics. Any attempt to measure a quantum system inevitably disturbs it. So if a third party, let's call them an eavesdropper, tries to intercept the quantum transmissions and extract the key, they would unavoidably disturb the quantum states. This disturbance is not just a minor inconvenience, it's a big red flag. The sender and receiver can detect this disturbance and immediately know that their communication is being intruded upon. This is like having an inbuilt alarm system that goes off the moment anyone tries to spy on your conversation. Now that's what I call secure communication. But just like any revolutionary technology, QKD is not without its challenges. The technology is still in its infancy and requires highly specialized equipment, like single-photon detectors, which are not yet widely available. Moreover, maintaining the integrity of quantum states over long distances is a significant hurdle. On top of that, there's the issue of quantum hacking. Yes, as futuristic as it sounds, quantum hacking is a real concern. Sophisticated attacks could potentially exploit weaknesses in the physical implementation of QKD systems, bypassing the security offered by quantum mechanics. Despite these challenges, the potential of QKD is immense. It could revolutionize how we secure our online communications, providing a robust defense against the disruptive power of quantum computers. However, the transition to quantum encryption methods isn't without its challenges. The transition from classical to quantum encryption methods presents a window of vulnerability. Now this is where things get a bit tricky. You see, whenever we're talking about shifting from one system to another, especially something as colossal as our internet security infrastructure, there's always a risk of something falling through the cracks. Imagine a bank trying to move all its gold from one vault to another. During the transition, there might be a moment when the gold isn't fully secured. It's the same with shifting to quantum encryption. There's a period where our conventional encryption could be compromised before quantum-resistant alternatives are fully operational. This transition period isn't something that can be rushed through. It's like crossing a chasm on a tightrope. It requires careful and deliberate steps. Because if we don't manage this transition properly, we risk exposing sensitive data to potential threats. Now, it's not all doom and gloom. This transition period also gives us an opportunity to rethink and redesign our security infrastructure. It's a chance to build something stronger and more resilient than what we've had before. But we need to be vigilant. We need to ensure that during this period, our communications, our transactions, our data are not left unprotected. This isn't the only area where quantum computers could have a significant impact. Quantum computers could also disrupt blockchain technology, which relies heavily on cryptographic algorithms for security. Blockchain's strength lies in its cryptographic hashes, creating a chain of blocks where each block contains a hash of the previous one. This ensures the immutability of the chain and secures the integrity of the distributed ledger. Now imagine if a quantum computer, with its immense computing power, could break these cryptographic hashes. This would undermine the core strength of blockchain, potentially compromising the security and immutability of the distributed ledgers. However, it's not all doom and gloom. Just as quantum computers pose a threat to blockchain, they also offer potential solutions. Quantum-resistant cryptographic algorithms could be implemented in the blockchain to secure it against quantum attacks. But the transition to these quantum-resistant algorithms would need to be managed carefully to avoid any vulnerabilities during the process. So how can we mitigate the risks posed by quantum computers? To protect against the threats posed by quantum computers, organizations need to adopt cryptographic agility. This concept is all about being nimble and swift in the face of quantum advances. It involves the ability to quickly switch to quantum-resistant algorithms as and when required. In the ever-evolving world of quantum computing, cryptographic agility is the secret weapon. It's like a chameleon, changing its colors to blend into the new quantum environment. To do this, it requires updating cryptographic protocols, software, and hardware across the internet infrastructure. This isn't a small task. It's like changing the engine of a moving car, but it's a necessary one. Without cryptographic agility, we risk leaving the door wide open to potential security threats. In conclusion, quantum computers have the potential to both break and secure the internet. It's a game of cat and mouse, and cryptographic agility is our best strategy to stay one step ahead.